Hello, my name is Tyler Dean. This is my first video problem for linear algebra at Hiram College. Just a quick recap today. During class, we had a problem where we had to connect or use two vectors which were represented by a hoverboard and a magic carpet with their vectors given of 3 and 1 and 1 and 2 for the respective modes of transportation. And the goal was to get to a certain location, which was represented by 107 and 64 today during class. And the goal was to see if we could get to that certain location. Then the other goal was to get to him anywhere to see if he could hide or not anywhere on the playing field. So we discussed it over in class, and what we came up with was, first we have our vectors written down. So then we had to graph this, which was represented by our graph. This is just a very simple graph just to give a representation. So we did find out that you can get to Gauss's original location. Then if he was anywhere else, he technically could not hide due to the fact that these are vectors. And a good thing about these vectors are that they can either be positive or negative, and they can also be used in any combination possible that we want. So that meaning between these two lines, by those definitions, between these two lines, anything between these two lines currently we can get to, which is a good thing. Now, since we can also use them as positive or negative because they are vectors, we can technically go backwards using these lines in any combination or order. So we can use the blue vector to come back down off the red vector. So we could do this. Then use the combination between them. Just keep doing that. We can zigzag all around. Just negative, back up, come across in parallel. Just like that. We can use any combination of these vectors to get to anywhere in the playing field. So Gauss cannot hide. Then to show this algebraically using claims by vector notation and linear combination vectors. So first we knew we needed 4 variables: x, y, w, and z. X and y are like our positive vectors. Then w and z are our negative vectors, just to get to Gauss, and that's what we equal. So to put it in more of a simplistic notation, we have our x1, x2, x3, and x4 with all the same vector values to get to Gauss. Then to put it into the linear combinations of vectors, such as a linear equation, we took those vectors with their x's and just put them with their respective numbers and their x and their y's. And that's what we can use to get to Gauss.